So we talked about bounded synthesis yesterday. And the idea of bounded synthesis is, of course, that we introduce this bound on the size of the implementations that we are willing to consider. So rather than looking for an arbitrary implementation, we look one with at most n states. And the approach here was to go from the LTL formula to a universal Kobushi automaton, which defines a constraint system. And we looked into various types of constraint systems, SAT, QBF, DQBF, that then can be solved by an efficient solver. So I called this a Zafra-less construction yesterday. I think I should call it a Javier-less construction maybe, because indeed we're not going through deterministic automata as usual in synthesis, but rather we only go to this simple step to a universal automaton, which is algorithmically the same step as going to a non-deterministic automaton. Now, the encoding of the existence of a implementation is fairly straightforward. We simply look, we take some representation of the states, such as the natural numbers, and then we look for a function that represents the labeling, another function that represents the transition function. And what we add is a annotation that ensures that we don't get an arbitrary implementation, but one that actually satisfies the specification. So then I showed you a few experimental results that indicate that, at least in terms of runtime, this is a very good solution. What was a bit disappointing was that the fully symbolic encoding, which goes to DQBF and treats everything symbolically, namely the inputs, the states of the implementation and the states of the automaton, actually performs badly. The optimum right now seems to be the input symbolic encoding, which treats the input symbolically, but the states of the automaton and the states of the automaton explicitly, right? And somewhere in the middle is the encoding that treats the states of the implementation symbolically and the input symbolically, but still treats the automaton explicitly. So, yes?
This is a comment that this is a phenomenon that shows itself in other contexts. Even in model checking, turns out that dealing with automata explicitly, other than symbolically, give you better performance in model checking.
Yeah, I think Moshe is saying that appears in other contexts too, right? Which is the case, but here it's really, I would say, disappointing, because there is a straightforward translation from this problem to that problem. So you would expect that the tool would do something better, right? But so all I'm saying is, if you're working in this area, this is an exceptionally low-hanging fruit to do something better. Yeah? Okay. There's a general movement in this direction for symbolic methods. So, this line certainly was more like this a few years back, and the SAT line was the optimum. But you would expect that now the QBF line is the best, and in a few years, this line I would expect to be the best approach. In any case, the most striking benefit of going to the bounded approach, of course, is the quality of the implementation. So this is hands down better than the traditional approach. So every point on this graph is a benchmark, and you see that pretty much all of them are far away from the line where traditional synthesis and bounded synthesis perform equally well, and a lot of them are actually, orders of magnitude better. Now, I want to emphasize that bounded synthesis is still a decision procedure, right? Because you might get the impression, we have restricted the problem and now we're only looking for small implementations. But of course, you can look for implementations and for counter strategies at the same time. So, in fact, we do that. So for every bound, you look if there's an implementation of this size, and you look at the dual problem and look if there's a strategy for player one that would refute the existence of an implementation. Now, while your bound is too small, you may not get a solution for either question, but eventually one of the two players will win. How do I know that? Well, I can go back to our original construction via the parity games, and from there I know that there is either an implementation or a counter strategy with at most doubly exponentially many states. Why is that? Well, the parity game has doubly exponentially many states, and one of the two players has a winning strategy, and in fact a positional winning strategy in the parity game. So if I increase my bound sufficiently high, then I will hit that strategy, right? Of course, I don't want to wait until I hit that doubly exponential bound, and in pretty much all cases, I will find the strategy way earlier than that. But that consideration guarantees that my approach will terminate.
So did you do a comparative number on a CACHA on unrealizable formulas?
Of course, yes. So, yeah, I don't have them here, but yeah, I mean, they're the benchmarks that have realizable and unrealizable benchmarks, and then there's the synthesis track in the synthesis competition where you essentially have realizable benchmarks because, well, the challenge is to get to small implementations rather than to check realizability. In fact, I think in a moment I'll have a slide with exactly that comparison in the setting of bounded cycle synthesis. So let's discuss it then. Anyway, I think to me that is sort of the real message here that, I mean, we can't avoid the doubly exponential complexity because indeed there are examples where there is no smaller implementation, but in many cases the solution is way smaller. And then we want to avoid constructing the whole game arena, right? We want to find the small solution fast if it exists. If it doesn't exist, then the fundamental complexity of the problem, of course, hits us. All right. So since we saw such a beautiful demo, let me at least also show a web site. So we have a tool implementation, of course, of bounded synthesis, and you can play with it by going to our web page. What it does is you enter a specification, typically structured into assumptions and guarantees, but you can use all of LTL. There's also a button with a nice collection of examples, so you don't have to start from scratch. Then you select a search strategy. So this is how do you want to increment the bound, right? So one solution is to go 1, 2, 3, 4, 5. Another solution is to increase the bound exponentially and therefore hit the bound quicker if it's a large bound. Then the back end, there you have various encodings. Here we have this input symbolic encoding. And then in terms of output, you get, well, you can have a graphical representation, but of course that only makes sense for tiny examples. You can also directly get Verilog code or SMV code if you like. Yes, please. Yeah, I mean, not on the web interface, but sure you can do that. Yeah. So I should point out in general, BOSI is just a modular framework. So you can plug in your favorite solver, even your favorite encoding if you want, because you might not use a propositional encoding. You can also plug in your favorite automaton generator and whatnot. It's just meant to put things together. And of course, we have predefined plugins for the best tools we know, right? But this is also meant as an experimentation platform where you could try out your new DQBF solver or so, right? Because it sort of immediately gives you access to a lot of benchmarks. All right. Then the last comment I want to make about bounded synthesis is that you, of course, want to go beyond just optimizing the number of states. So I showed you yesterday the synthesis of this T-burst 4 component in the AMBA protocol, which, as I discussed yesterday, is responsible for handling burst transmissions of length 4. And this is what you get with standard synthesis tools. If you use bounded synthesis, you get this. So this has a minimal number of states. But it's still pretty tricky to understand what's going on. In particular, to identify the 4 phases of the protocol is difficult. And now, if you additionally minimize the number of cycles, then you get this. And this is fairly close to what you would write by hand. So this is what we call bounded cycle synthesis. So it sits on top of bounded synthesis. So we still optimize the number of states, but you have the observation that even if you have a minimal number of states, then the control structure in the graph may still be fairly complicated. So you would want to add additional parameters, and what bounded cycle synthesis does, it minimizes the number of simple cycles in the graph. So in some sense, the number of cycles is an even more interesting parameter than the number of states, because the number of cycles is exponential in the number of states. And in fact, there are LTL formulas that force you to have a triply exponential number of cycles in the graph. So as you can imagine, if you have such an explosive parameter, if you limit that parameter, then you're really making the constraint solving problem tight. And this is what's happening here. So yeah, now I think I have the experiments that I promised Moshe. So let's see how to read that. So these are just a number of standard benchmarks. And then you see the standard synthesis with Acacia, then the bounded synthesis, and then the bounded cycle synthesis. So, I mean, obviously, the number of cycles already drops dramatically as you go from standard synthesis to bounded synthesis. So, I mean, there we have more cycles that we could count. Here we go down to, say, 8 in this example. And with minimizing the number of cycles, we go further down to 4. So, I mean, the most dramatic benefit obviously happens.
Why do you want to minimize the number of cycles?
Because that makes the control structure simpler. You avoid nesting of cycles, because that gives you, well, a larger number of simple cycles. So, generally speaking, I mean, just the visual difference is this versus that. I mean, the two are not. I mean, not the size of the graph is not different, right? But if you want to understand what these cycles mean, then here you have much fewer of them, so that's an easier task. Yes, please.
So whether there are a lot number of cycles is just, I mean, it's just for human beings. Since we will think this is simpler than that, just because when we view this station, we think it's simple, but in terms of implementation, I think it should be more practical to consider like delay or some after use. So using number of cycles as an objective function during synthesis, do you consider it a good idea? Or I mean, since just like you just choose this as an objective function and try to optimize it, but does this correspond to final quality of your implementation? Yeah. Okay.
So the point raised is. There are other parameters we could consider, in particular in circuits, the delay, the depth of the circuit, whatnot. And this is absolutely true. I mean, in the end, we want a good solution, and what a good solution is of course, subject to debate. I would say that these tools have a purpose if they do better than a human programmer in some way, or they do what would take the human programmer some time in very efficiently. So I would want the solution to be, well, good in some way that also a programmer would try to achieve. And certainly, I mean, this corresponds much more to well-structured code than the spaghetti code on the other slide, right? So this has value, because then we can look at that solution and reevaluate that is actually what we were looking for, right? Versus, I mean, you certainly don't have a chance here to say that this is correct. And this is terribly important in synthesis, because we start with the specification, and we need to be sure that what we specified was right? Because if all we know that this satisfies the specification, and we don't know if it is what we wanted it to be, versus here we can revalidate and say, yeah, this is what we had in mind, or we have to add a specification. But I completely agree with you that we should consider more parameters. And the interesting question, of course, is what parameters come with what cost, and what can we actually do? So this, I would say, is a first step in an agenda that tries to optimize, or first define what good solutions are, and then see how they can be incorporated in the constraint system. Okay, now here the time is in this part for the successful bound. So obviously we try many bounds, and this time here is only for the bound where we were successful. And this is the time needed for the last bound before that. So when the bound was just a little bit too small to find a solution. So in most cases, the effort for doing the minimal cycle synthesis is actually not that different from the effort for just doing bounded synthesis. You see that the numbers are fairly similar, but there are outliers. So for example, the T-burst4 component takes significantly longer to minimize the number of cycles than just to find the bounded state solution. What's also interesting is that sometimes the last bound before the solution is found has a horrible running time. So I think both have the simple explanation that we have a much stronger constraint problem now, right? So the closer you are to actually finding a solution, the harder it becomes to refute the existence of a solution. And that is why here the actual solution space is much smaller in the bounded cycle version. And if you're almost there, then it takes really long to refute that. All right. So
consider running these tools in parallel with just the first one to terminate.
This is exactly the motivation behind this analysis, right? So normally I would accumulate all the running times for all the bounds, and just taking the successful running time corresponds to the intuition that I'll run all bounds in parallel and just stop as soon as I hit one. Yeah, I think that is absolutely what you have to do, because otherwise you run into this problem. Okay. So let me get to the last part, which revisits the issue of synthesizing distributed systems, which we talked about on Sunday already. So this is the issue. We additionally consider a architecture, and we want to find a solution that corresponds to the architecture. And what I want to do now is, first of all, get back essentially to Sunday and explain a bit more precisely what we mean by the Pnelli-Rosner model. Then talk about bounded synthesis and show how this can be solved using bounded synthesis. And then probably very briefly talk about newer developments that go beyond the Pnelli-Rosner model. So we have this architecture, which is a graph where the nodes are processes, and the edges represent shared variables between those processes. So here we have process 1, who writes to Boolean variables B and C, which are read by process 2. Process 2 in turn produces D, which is read by process 3, and so forth. So the edges describe the communication structure by referring to Boolean variables. Now, in the Pnelli-Rosner model, we build a strategy for each individual component. So, for example, process 3 here reads in input D, produces output E. So its strategy tree would be labeled with the values of E and would branch according to the possible values of D. So for each process P, we have an implementation with input variables IP, output variables OP, and that is a strategy tree that branches according to the values of IP and produces the values of OP. Once we have such a local implementation for every process, we just put them together and we get one big tree which branches according to the inputs that come from the environment. and is labeled with all variables in the system, right? And this is the computation tree that branches according to the global inputs and is labeled with all variables, and the implementation is correct if that computation tree satisfies our specification, say our LTL formula. Now, in principle, you could say, let's just synthesize this tree, right? This is what we know how to do. But unfortunately, that would get you into trouble, and the trouble is that the processes only have partial observation, right? So, for example, in this pipeline here, process 2 sees Y, but he doesn't see X immediately, which means that the output set is only allowed to depend on Y, but not on X unless the value of X is somehow reflected in Y. So in this example, we have two paths that differ, of course, in the value of X along the path, but that have the same values of Y, right? There's Y0, Y0, here Y1. So process 2 doesn't have a chance to distinguish these two nodes of the tree. So if the output of process 2 would be different in those two nodes, then that would be inconsistent. It actually has to produce the same output whenever it can't distinguish the nodes. So correct implementation would need to have the same value for set in these two nodes. Okay, and we already talked about the problem that this is undecidable. So in fact, the architecture considered in the proof we looked at on Sunday was this, with the two independent processes. Actually, the general criterion whether or not the problem is undecidable is whether there's an information fork, which we call a situation where there's a pair of two processes that each can derive something about the input from the environment that the other process can't derive. And it's actually the case that whenever you don't have such a fork situation, for example, if you have a ring or a extension to the ring, so in that case, we have a complete order on the informedness of the processes, then the problem stays decidable, right? And this was a long history of results that led to that. So the situation here is that if you have an architecture with a single process, then the problem is 2x time complete. This is the problem essentially that we have been looking at all along, with the mild extension that the environment might make choices that our process doesn't observe. But this doesn't affect the complexity. Then if you have a pipeline architecture, that is, you have this sequence of processes, which means that process 1 is the best informed process, then you have process 2, and process 3 is the least informed process, then you get non-elementary complexity. And of course, if you have something as simple as a two-process arbiter, then you essentially have the situation from the Pinelli-Rosner paper, that is, each of those two processes has access to some information that the other one doesn't have, and already this simple situation is undecidable. So that is the pretty depressing state of affairs in the Pinelli-Rosner world. Yes, please.
Why doesn't have process 1 access to the information of process 2? Couldn't just process 2 just pass the information over?
Okay, yeah. So Salomon made the observation that in the Pinelli-Rosner paper, these edges here were actually missing, right? Or at least in the example I showed on Sunday, process 1 had an output, process 2 had an output, and they couldn't reach each other's output. So if you're lucky and process 1 is allowed to give all the information to process 2 and vice versa, then this collapses to the monolithic synthesis problem and becomes decidable. The problem, of course, is that the specification can easily disallow that, for example, by stating that the output on these edges is encrypted. So you take a stream of bits coming in from the environment and actually pass on the XOR of your output with that stream of inputs, and then there's no way for the other process to recover what information you wanted to to transmit. So then, no matter what the original specification was, the information giving to the partner is null. Okay. Yes, so this of course leaves very little for actual synthesis algorithms. I mean, this situation of course is important. It could well be that you're dealing with an environment that you can't completely observe. For example, you see reality through sensors, so there's more going on in the reality than what is directly the input of the process. But beyond that, things simply become undecidable or too expensive. So let's see what we can do with bounded synthesis. Well, with bounded synthesis, the answer is boring, but much more friendly. We have NP all over the place. It really doesn't matter what the architecture is. Now, why is that? Well, we do the same thing again. We represent the solution by building a finite state machine with states, a labeling function, a transition function, and a annotation that proves that all this is correct. So far, exactly as we have done it before. If we would stop at this point, then we would have the problem that we would get inconsistent solutions, right? Trees where the output depends on things it should not depend on. Therefore, we need to add a little bit more. Well, we add a local transition system for every process. So again, this is a transition function that only depends on the local input, and that goes from a local state to another local state. And then we need to connect the local transition system with the global transition system by a projection. So in other words, we have two representations of the solution. One that is the product of the processes. And in this product, we prove that we satisfy our temporal specification. And then we have the local copy that says that actually each strategy for each of the processes only depends on inputs that the local process has. Now, if we have two representations of the same thing, then of course we need to make sure that they are consistent. And this we can do with extra constraints. So these constraints say that there are essentially three ways to compute the same thing. So we can take a global state, project it on to process 1, and then apply the local transition of process 1. For that, we need the input from the environment, that is R1, and also the input that's received from the second process. So for that, we project the global state to the second process and read out what output is produced by the second process.
Why do you need global state?
We need the global state because the annotation refers to the global state, right? So I need to prove that my LTL formula is correct for the composition of the local strategies.
Yes.
And this I do by annotating the product state space. Yes, please.
You can take like a tuple of local states and stuff for local states, right?
Yes. So the consideration is we could take the tuple of the local states as the global state. That's absolutely correct. Yep. We still need to make sure that the transitions are then also composed along the local solution, but obviously we can't do that. Let me just state the consistency requirement. So I can see how I get to the successor in the local state space. I can see how I get to the successor by taking the successor in the global graph and then projecting back to the first process. And of course, I can also see what would happen if I had a so here I have the actual input in the global transition system, say R1 and R2. And of course, since process 1 can't observe R2, the result needs to be the same if I make a global step to not R2. and then project back to the first process. I mean, maybe to Ayrat's point, a great advantage of having a separate representation of the product system is that you have a chance to optimize on that one too. But obviously you can do a tuple representation of the local state space. All right. So with that, we can essentially solve the bounded, the distributed synthesis problem. Of course, this time we don't have a decision procedure in general because it's an undecidable problem. If you happen to be in one of the decidable fragments and you have an upper bound on the size of the strategy, then you can, in principle, limit yourself to bounds up to that bound, yes. But of course, this is of mere theoretical interest because we will never be able to solve this for huge bounds. So again, the only case where this works is where you have a reasonably small solution for the processes and for their product. All right. So I want to use the last few minutes to speculate a little bit about the situation beyond the Pnelli-Rosner model. So in a way, the situation is unpleasant because we have the bounded synthesis solution, but really no decision procedure. And the reason for that is this expressive power that results from having distributed information. So an obvious question to ask is whether the Pnelli-Rosner model of distribution, which works with partial observation, every process observes a subset of the variables, is the one we actually need. And the argument has been made that actually in many applications that is not what we need. Instead, we could go to a causal memory model. So the causal memory model works very differently to partial observation. The idea here is that the processes either are independent of each other, in which case they communicate nothing, or they synchronize, in which case they can exchange an arbitrary amount of information. So in a way you could say that the Pnelli-Rosner model always sees the world through a filter. So in every step it sees a projection of what's actually going on. In this model, if processes run independently of each other, then they don't know what's going on in the other process. But if they go through an explicit synchronization step, then it's your choice as the programmer how much information you want to learn from the other guy. So you could imagine that as having a programming interface, and you could learn as much as you want through that programming interface, but you have to synchronize with the other process, which you may not want to do or may not be able to do. But when you have decided to synchronize with the other process, then you might as well ask as much as you want. So the model says the processes communicate their entire causal history, everything they know, to each other during each synchronization. Formally, after the synchronization, they have the same causal history. The same things have affected them as they went into the synchronization. And my way of thinking about it is that we now abstract from the actual content of a communication. The synthesis algorithm is allowed to choose what is the content of the communication. The restriction is when you're allowed to actually synchronize and hence exchange this information. Now, of course, this is a completely different model to the Pnelli-Rosner model, and that has given rise to the hope that, well, since our undecidability proofs don't carry over, maybe this is not undecidable after all. Now, whether or not that hope is justified is an open question. We don't know what the decidability of the causal memory synthesis problem is, but there has been a lot of results that are encouraging. So you have a lot of sort of special situations where the synthesis problem becomes decidable in the causal memory model. So in particular, if you're if the communication between your processes is of a tree-shaped nature, so there is no cyclic communication between the processes, but you can order the processes in who communicates with whom into a tree, then the problem becomes decidable. There's a very recent result from FST-TCS this month, which says that for 4 players, the problem is decidable. It doesn't extend to 5 players, but at least that's a very surprising result. I still have to fully understand that. I've looked at cases where the complexity is of a reasonable, somewhat reasonable, because most of these results just talk about the principal decidability, which means you have non-elementary algorithms and in some cases non-elementary lower bounds. So 2 cases where you get to X time, which I would consider reasonable, is when either the environment consists of a single process or the system consists of a single process. So, I mean, I'll have to say more cleanly what that means, but essentially it means that if your environment is monolithic, then your system can be distributed, or if your system is monolithic, then you can have a distributed environment, so you can get your information from multiple sources in the environment. And in these 2 situations, you essentially come to the complexity of the non-distributed synthesis, which I think is very exciting because both of them model really important situations that you couldn't take care of with standard synthesis. So, yeah, let me maybe just, yes, please.
I don't see it. How does it relate to what I consider normal distributed protocols? Normal distributed protocols are aimed at having typically each node a finite machine.
Yes.
Right? So, could this give you, for example, finite machines at every node? I don't quite understand them.
Okay.
Yeah.
Well, I've been very abstract and hand-wavy, so your question is absolutely justified. So Moshe's question is, will I get a finite state machine at the end? Yes, I will get a finite state machine at the end. The only thing I'm changing is on what knowledge the processes are operating, right? So far we said, okay, there's this this history of observations, and this is defined by a projection on the actual state history. Now we're saying that I'm allowed to look at the causal history. So I have a concurrent situation and I look at the causal past. Let me give you an example to make this more clear. My problem is all these models are slightly different, and I won't do justice really to these results now by giving you one example in one of them. But please bear with me. I just want to give you an idea how this works. So I will, of course, jump to my favorite way of formalizing these things, which are Petri games. So in a Petri game, well, you know how a Petri net is, and the situation here is that we have 2 types of tokens. So the red tokens represent the environment, the blue tokens represent the system processes. And, well, I consider each of these tokens as a separate process, so they need to make their decisions based on their own causal past. So we have environment player, we have multiple system players in this example. We have local transitions, so this token can move from here to here. This is a transition that doesn't affect the other player, so the other player will not know that this transition happened. And we have synchronization, so these are transitions that involve multiple players, and that means when that transition is taken, then the causal history is shared between the resulting tokens. So whatever happened here and whatever happened here becomes knowledge for the future in those 2 tokens. So Moshe actually has seen this before, but it's my favorite. I mean, it's the smallest example that fits on a slide, so it's nice. So it's a distributed alarm system. Say you have 2 buildings where you install separate alarm systems, and the property you would like to have is that when a burglar this gentleman enters one of the two buildings, then in both buildings an alarm should ring, and that alarm should indicate where the burglar is. So this means the alarm goes off in this building, and the burglar is actually in this building. This means the alarm goes off here, and the burglar is actually over here. And likewise, this means the alarm goes off here, and the burglar is actually there. The alarm goes off here, and the burglar is also here. So we have two processes in the two buildings, which obviously need to exchange information because they wouldn't know otherwise if in the other building there's a burglar. So with red here, I've indicated that the environment player, the burglar, has chosen to enter the left building. So when that happens, our alarm system in the left building can synchronize with the burglar, which means that now the left alarm system knows that a burglary has taken place in his building. Our alarm system in the other building is still in its original position and has not noticed anything, right? It could, in principle, decide to take this transition and go down here and then go to one of these two choices and raise an alarm, but that would be a really bad strategy because then it would raise an alarm no matter if the burglar entered the building or not. And it also wouldn't know where the burglar is. So let's say our token on the left has been moved here, so it has synchronized with the burglar. Now the left alarm system knows that the burglar is on the left. It could therefore, so we're here, it could therefore go down and raise its alarm. But if it did that, then the right alarm system wouldn't have a chance to raise the right alarm. So what it does instead is it goes through this synchronizing transition, which moves the right token to this place. At this point, both alarm systems know that the burglar entered the left building, and therefore both of them can go to the right target place and raise an alarm. So you see that it was crucial that the strategy for the left alarm system included the synchronization step, because only then did the right alarm system have a strategy to actually identify the correct alarm. You could model this in the Gnede-Rosner model, but then you would have two processes that each have access to some information, namely the burglar is left, the burglar is right, that the other one doesn't have. So this would be a classic example of an architecture with an undecidable synthesis problem. By contrast, if I formulate it in this way, I have an XPLAM algorithm to find these strategies. Of course, the limitation, the essential limitation is that this player doesn't have a chance to give a partial information to the other player, right? If it decides to synchronize, then this token gets taken here and in the process learns everything that happened on the left side. So this is a modeling restriction, but at least for this example, this is exactly what you need, because there's no point in forbidding the alarm systems to communicate a certain information. Yes, please.
I have a question about the last transition. So why from replace P8, for example, if the token chooses necessarily to go left?
Sorry, what was the question?
There is this place P8 and how the token chooses where to go after that.
Mm-hmm.
Repeat the question.
Will do. So the question was, there's this place here, and how do I know whether I should go left or right? That is your question, right? So for example, if the burglar had gone to the right-hand side, then this would be the wrong strategy. I would have to go to the right.
Yes, but how does this Petronet ensures that, I don't see any synchronization.
Okay, there are 2 points to your question. So the question was, how does the Petronet ensure that? So first of all, I haven't told you what the winning condition of the game is. And the winning condition is to avoid having wrong answers. So for example, if there's a token here, but the burglar is here, that would be a bad situation. So we list these bad situations, and you can see that as having another transition that goes from here and then goes to a bad place. So we list all the bad situations, And the other question you had was, how do I make sure that this doesn't happen? How do I make sure that I don't reach a bad situation? And that is, of course, the job of the synthesis algorithm. Now, the first observation is you might be tempted to look for a strategy as simply an annotation. If I'm in this place, I take this transition, for example, which, of course, as you pointed out, would be wrong in this situation, because there are situations in which when the token reaches this place, I have to go left, and there are other situations where the token is here and it has to go right. So the point is, the token has more information than just on what place it currently resides. It has access to its causal history. The formal way of saying that is that we're not actually looking at the Petri net, but at the unfolding of the Petri net, which means that all these situations where we are in PA, but we got there by a different causal history, actually correspond to different places, right? So I take the original net, I unfold it. This is now conceptually, because this may be an infinite graph, of course, but I unfold it so that there are no two places that have the same causal history. And once I have done that, then I can say, okay, this is the causal history where the token has moved here, right? There was a synchronization with the burglar on the left-hand side. Therefore, in this situation, I have to take the left transition. However, if I came from here, I synchronized with the other alarm system, and I reached PA on this history, then of course I have to take the right transition because, well, the burglar is on the right, right? So the unfolding essentially gives me all the situations in which I'm allowed to act differently. I'm not allowed to act differently if I have the same causal history, but of course if I have a difference in the history, then I'm allowed to make a different strategic choice. So what then happens is a strategy is simply a subnet of the unfolding where I'm not allowed to restrict what the environment does, but I'm allowed to restrict what the system players do. And then I get again a possibly infinite Petri net that has the desired property. Namely, in this case, no judgment will be wrong, right? If I'm here, then the burglar will also be there. Yes, please.
Is it assumed that always at most one token in each place?
Yes, this is a safe Petri net. Yes. So I should say that, again, the models people have looked at differ. Looking at safe Petri nets is my favorite way of thinking about things. They don't have to be safe. It just becomes very quickly undecidable if you don't have safe Petri nets. A very popular model is also asynchronous automata, which you could, well, there are some major differences, but one of them is that you can always separate the processes into separate parts of the net, right? So you never have the generation of tokens or the deletion of tokens. But let's not get into these details. Yes, please.
At what level is the distributed synthesis operating here? You think of every node as a separate...
No, every token. Moshe's question is, what are the processes, or what is the distributed problem here? The tokens are processes.
The token.
Yes.
The causal memories, where they are in the... For you, the causal memories, where are they in the vector? That's the memory for you.
Causal memory, you could state, is the place in the unfolding. So it's not in the original net. So in the original net, I wouldn't know where I came from, right? But in the unfolding, I have that information because every place has a unique causal history. Okay,
The various results, I mean, Javier is here, but bounded unfolding, are you making use of such results?
So, yeah, I mean, the algorithms here are based on classic Petri net theory. Concepts like cuts and so forth make a reappearance. It's just that the problem is harder because I can't just look for a repetitive situation in the unfolding and say, now I'm done, because it might be that the global state is the same, but the knowledge of the players is different. So I can only delete redundant sections from an execution when actually the knowledge of all the players is the same and the marking is the same. So, but you could say it's an extension of these ideas. So maybe just to finish the story here. So I have my strategy, which is this subnet, which still leaves all the choices open for the environment tokens. So the burglar can still go left and right. And a play is now, again, a subgraph that resolves these decisions of the environment players too. So for example, this would be a play where the environment player chooses to go right. And of course, there's another play where he would have chosen to go to the left. And in order to win the game, we need to win in all plays. There was a question. No? Good. So I guess this refers to Moshe's earlier question. Now we get a strategy which is a subgraph of the unfolding. So if you want, this is still something global. What you can do is you can distribute that into a parallel composition of local controllers for each of the tokens. So under some technical assumptions, in particular that the net is concurrency preserving, so you can actually track all the tokens and assign them to processes, you get this property. So you take your global strategy and project it out into a process for the environment and one for the left, in our example, for the left alarm system, and one for the right alarm system. Now, these projections have transitions that occur in both nets. So, for example, this TAA was a synchronization between the two alarm systems. So they occur both. And if you would compose this back into one PetriNet, then I mean the predecessors of TAA from both graphs would become the predecessors of the transition in the joint PetriNet, and likewise with the successors, right? So this and that would also be successors of transition TAA. So this is the notion of composition in PetriNets, where you simply combine the sets of places, the sets of transitions, and you get a net again. In our terminology, this means that this is actually, a synchronous, this is a handshake. So I can take this transition here if and only if I take this transition here. So that means in the joint execution, the two processes make this step jointly, right? But yeah, these are then the processes, and in general, these might be infinite state processes. But of course, for the decidable situations, we then get the property that you get a finite net as the solution, which means that the number of symbols that you have here for the synchronization is finite, and that the state space of the individual process is finite. So this is the 2014 result that says that you can actually reduce these games back to parity games, such that the original game is won by the system players if and only if player 0 wins the Büchi game. And then you take the winning strategy from the Büchi game and build from that a winning strategy for the parity game, for the Petri game. Excuse me. So very quickly, Manuel Gieseking wrote a tool based on this construction. It's called Adam. And so this does a BDD-based representation of cuts and uses a lot of optimizations from PetriNet theory, in particular invariance, to restrict the, to have a pre-computed range of places where a token can be, and then a optimized representation of cuts based on that. And so the interesting thing about this study is that it actually scales to something like 10 independent agents on case studies that are not terribly complicated, but that model somewhat realistic ideas from manufacturing. So the performance of atom looks somewhat like this. So obviously we have exponential curves, but there is actually a non-empty stretch where we can look at distributed problems, right? So it depends on the benchmark how far we get to the right, but we can actually synthesize distributed strategies. So this is encouraging. It's by far not the end of the story because this is a very restricted case. Also, it's clear that you would want in some way to combine causal memory ideas with partial observation ideas. In my view, this causal memory idea is always appropriate if you're looking at actual processes that you're programming, right? So if you're writing different processes, then you want them to run as independently as possible because that's good for performance. But if you decide to synchronize, then you might as well make the most of it and transmit the entire causal history. However, it's not appropriate if you model a robot that looks at its surroundings through sensors, because that robot has no chance to get the full information. He only gets a projection available in these sensors. So for realistic applications, you for sure will need aspects of both. But this is, you know, at an early stage. I think we're getting exciting results for special cases, but whether or not the complete problem is decidable or not, and whether there are whether there's a large landscape of fragments with good complexity is certainly open. Yeah.
Where do Petri games come from initially? Is it from the synthesis of cell spectra here? How do you construct Petri games usually?
No, in this case, the question was where does the game come from? And it is in a way comparable to where does the architecture come from. It's a restriction on the information exchange between the processes. In the Pnully-Rosner architecture, there would be a permanent projection on which variables are observable and which are not. In the case of Petri games, that would be dynamic, saying that under these circumstances, you're allowed to synchronize. For example, if you have robots, they might only be able to synchronize if they're close to each other or so. And that is defined by the game, right? Because if we allow arbitrary synchronization, then we are, of course, back in the original synthesis problem with full, the monolithic synthesis problem, right? So the real question here is how do we restrict things so that it becomes more realistic and we can still solve it.
We ready to close?
Let me conclude. So my conclusion is very simple. We've looked at a really hard problem. The complexities are staggering and might give you the idea that there's nothing that can be done. And yet, we're collecting more and more of these small, really small success stories where something interesting gets built. And I think this is very encouraging because it means that maybe these worst-case complexities don't tell the full story. And certainly, bounded synthesis gives an idea how such a solution could look like, because we do have pretty good and constantly improving solvers for NP problems. But this is certainly not the end of the story. NP is probably not an acceptable complexity for a real practical synthesis approach. So for me, the challenge now is to identify the right parameters. The number of states was one of them, but things like the dependency between processes and so forth might be another parameter that would allow us to identify really which synthesis problems are hard and which can be solved in a practical fashion. Thank you very much.